Hello grade 12s. Welcome to this lesson on photoelectric emission. Let's start with a bit of imagination. Later, you will see what this has to do with photoelectric emission. Imagine we are stranded out at sea. We cling to a rock as we wait for rescue. Which kinds of waves would we be more scared of? One big wave or many small waves? Of course, we'll be more scared of the big wave. One big wave is more likely to push us off the rock than many small waves. Big waves have a high amplitude. If many waves pass a point in a certain time, we say the waves have a high frequency. So we would be scared of waves with a high amplitude, even if their frequency was low. In other words, big waves, even if few hit us. We would not be scared of waves of a low amplitude, even if their frequency was high. In other words, small waves, even if many hit us. Now let's imagine that instead of us clinging to a rock, we have electrons that cling to the surface of a piece of metal. We shine light onto this metal. If light is a wave, which waves would be more likely to push the electrons off the metal? Waves with a high amplitude and low frequency, or waves with a low amplitude and high frequency? Surely, if light is a wave, we would expect the big waves to knock the electrons off, just as the big waves would be more likely to knock us off the rock. So what kind of light has a large amplitude and what kind of light has a high frequency? If light is a wave, its amplitude refers to how bright the light is. Dim light has a low amplitude and bright light a higher amplitude. Another term for a light's brightness is its intensity. Bright light is more intense than dim light. The frequency of the light determines the light's color. Red light has a low frequency. Blue has a high frequency, and ultraviolet an even higher frequency. Remember that frequency and wavelength are inversely related. So red light has a long wavelength and low frequency, and ultraviolet light has a short wavelength and high frequency. So remember, we said that big waves seem more likely to knock the electrons off the metal. This means that bright light, which has a high amplitude, should be more likely to knock electrons off the metal than any light which is dimmer. And that was what scientists predicted too. You see, it is possible to knock electrons off a metal by shining certain light on the metal. This is called the photoelectric effect. It is also called photoelectric emission. Photo means light, electric refers to electrons, and emission means being knocked off. Scientists predicted that bright light of any color would be more likely to cause photoelectric emission than dim light of any color. However, to their surprise, they found this was not so. Let's join Tony as he shows us what the scientists did and what they found.
Well, in 1885, round about that period, a very interesting discovery was made by Heinrich Rudolf Hertz, the man who in fact proved the existence of radio waves. What he also did was he found an effect known as the photoelectric effect. And in our laboratory today, we can actually show a very simple experiment, a very classical experiment, if you like, on this particular effect. Here we have a typical gold leaf electroscope, and I'm sure most of you have seen gold leaf electroscopes in your time, but just to give a brief explanation, what happens is that if I charge the gold leaf electroscope with some electrical charge, a static charge, be it positive or negative, the gold leaf within the glass enclosure here will simply open up to indicate to us that such a charge exists. Now, what we're going to do is I'm going to impart upon this electroscope a negative charge, and for that I've got a nice piece of fur here and a glass rod, and we'll simply rub this rod thus, and with a bit of luck, and in a lot of cases physics experiments tend to fail, but let's hope that this one works quite nicely. You will see now that as I bring the rod to the electroscope, the gold leaf stands out very proud. There we are, we've got a nice charge on there, and that hopefully is a negative charge. Now, first of all, let's expose that negative charge, if you like, and our zinc plate. I'm going to expose the zinc to ordinary white light. There we go, from a good old torch, and as you see, absolutely nothing happens. Let's see if it has anything to do with the intensity, because it might well be. For this, I've now got one of these really high intensity lamps used in filming, as we have in the studio, and there we go, we switch it on. I've now applied a large amount of high amplitude, if you like, high brightness white light, and still nothing happens. Let's now put the ultraviolet light in place, and look what happens. Your gold leaf discharges. You can actually see the gold leaf dropping from the near horizontal position back to the vertical. Now, I imparted onto the zinc a negative charge, electrostatic charge. When we exposed the zinc to ordinary visible light from this torch, nothing happened. The gold leaf tended to stand out, and as we applied the light, nothing occurred. It stayed put until we put this shorter wavelength source of light, this ultraviolet light, which is at around about a wavelength of about 390 nanometers, if you like. We placed this the source of light close to our zinc plate, and what in fact happened was that photons, very high energy photons from the ultraviolet source, struck the zinc plate and thus knocking off electrons. And so our negatively charged electrons were released, and of course discharging our gold leaf electrostates.
Thank you, Tony. So these findings are exactly the opposite of what we and scientists at that time predicted. Tony first shone white light onto the zinc. He started with dim white light and then used bright white light. White light consists of a number of colors. All of them have lower frequencies than ultraviolet light. Strangely, even the high amplitude white light could not cause photoelectric emission. The ultraviolet light did successfully cause photoelectric emission, even though it was dim. Ultraviolet light has a high frequency. If Tony had used a bright ultraviolet light, it would also have caused photoelectric emission. So what this experiment shows us is that it is the color, not the intensity of the light, which determines if photoelectric emission occurs from a metal or not. In other words, whether photoelectric emission occurs is determined by the frequency, not the amplitude of the light. That is similar to saying that the frequency of sea waves, not their size, determines if we are knocked off a rock in the sea. If that was true, we should be more scared of many little waves than one big wave. This is ridiculous, of course. So clearly, light cannot be viewed as a wave when we explain the photoelectric experiment. That is the conclusion which a young Albert Einstein reached and published in 1905. Einstein explained the photoelectric effect by referring to light as a stream of particles. These particles are called photons. He said that each photon carries an amount of energy which is determined by the light's color. So the energy of each photon is determined by the light's frequency. Red light has a low frequency. Photons of red light each carry a small amount of energy. Ultraviolet light has a high frequency. Photons of ultraviolet light each carry a lot of energy. To help us understand the concepts, here we represent each photon as an orange ball, where its size represents its amount of energy. However, we must remember that photons actually have no size or mass at all. Einstein said the intensity of light is determined by the rate at which the light source emits photons. A dim light emits few photons every second. A bright light emits many photons every second. Einstein suggested that when photons reach a metal plate, each photon gives all its energy to only one electron on the plate. If an electron receives enough energy to allow it to break away from the metal it is on, then it is emitted. Photoelectric emission occurs. If an electron does not receive enough energy to be emitted, it stays on the metal, so no photoelectric emission occurs. Let's use Einstein's ideas about light to think through the photoelectric experiments Tony showed us. First, Tony shone torchlight on the zinc plate. This is dim white light. White light consists of many colors, and so many different kinds of photons. Each of them, however, has a fairly low frequency. For simplicity, the photons are represented here as if they all have the same amount of energy, which is low. The torchlight was dim, so it emitted few photons every second. Can you see why no photoelectric emission occurred when Tony shone the torchlight on the zinc metal? Each photon which reached the metal gave all its energy to one electron. But this was not much energy, not enough to enable that electron to separate from the attractive forces the metal exerts on it. Next, Tony shone a bright flood light on the zinc metal. Again, this light was white, and so consisted of a number of low-frequency colors. So again, each photon did not have very much energy. Because this was bright light, it emitted many photons each second. When each of these photons reached the zinc plate, it gave all its energy to one electron in the zinc. Can you see why this did not cause photoelectric emission, even though the light was bright? Each electron still received too little energy to be knocked off the metal plate. Photoelectric emission did not occur. Finally, Tony shone a dim ultraviolet light onto the zinc plate. Ultraviolet light has a high frequency. This means that each photon carries much energy. The light was dim, so the light emitted few of these photons every second. When each photon reached the zinc, it gave all of its energy to one electron in the zinc. Can you see why the ultraviolet light did cause photoelectric emission, even though it was a dim light? Not many electrons receive energy each second, since not many photons reach the zinc each second. However, each electron which receives energy receives a lot. This is enough to knock the electron off the zinc metal. And what would have happened if Tony had shone a bright ultraviolet light on the zinc? Now more of the high energy photons would be emitted by the light each second, so more electrons would receive enough energy to be knocked off the metal each second. So photoelectric emission would still occur, but now at a faster rate. Einstein's explanation of the photoelectric effect won him the Nobel Prize for science. Why was his explanation so important? This explanation showed that light has a particle nature in addition to light's already known wave nature. This is called the dual nature of light. Dual means two. Here, it refers to light being both a particle and a wave. Einstein's explanation also established quantum theory, which refers to energy being quantized. This means that energy exists in discrete packages. Values in between these packages are impossible. Each photon carries a certain number of packages, quanta of energy. This is determined by the color of the light. Well, that's it for today. Don't forget to check out other videos in this series, especially the task video. Also look at the Mindset website at www.mindset.co.za/learn. Goodbye. Waves with a high amplitude, even if their frequency was low. In other words, big waves, even if few hit us. We would not be scared of waves of a low amplitude, even if their frequency was high. In other words, small waves, even if one big wave is more likely to push us off the rock than many small waves. Big waves have a high amplitude. If many waves pass a point in a certain time, we say the waves have a high frequency. So we would be scared of waves to electric emission. Imagine we are stranded out at sea. We cling to a rock as we wait for rescue. Which kinds of waves would we be more scared of? One big wave or many small waves? Of course, we'll be more scared of the big wave when it hit us. Now let's imagine that instead of us clinging to a rock, we have electrons that cling to the surface of a piece of metal. We shine light onto this metal. If light is a wave, which waves would be more likely to push the electrons off the metal? Hello grade 12s. Welcome to this lesson on photoelectric emission. Let's start with a bit of imagination. Later, you will see what this has to do with